Okay, in writing out a deduction rule for first order logic, we run into a bit of a problem. We can't have as simple a version of the deduction rule as for propositional logic. And this is essentially because of the presence of the generalization inference rule. The inference that generalization allows us to make is a valid one. Let's say it's sound, if you like. Because if A is valid, then so is for all xa, and vice versa, in fact. Okay? But if we could simply apply a version of the deduction rule without any conditions, that would let us prove from that inference A implies for all xa, right? We could assume A, from that prove via the generalization for all xa, then discharge our assumption A, and claim that we can prove A implies for all xa. But this formula is not valid. Why is that? Consider, for instance, an interpretation over the natural numbers. So over the domain of the natural numbers, where maybe A is the atomic predicate, or the atomic formula, let's say, even x, which is interpreted by our interpretation as meaning x is even. So in other words, this even is a predicate symbol that is interpreted by our interpretation as representing, as denoting the set of all even natural numbers. Then even x will have the truth value t if and only if x is an even natural number. Okay? Well, that's fine, but the fact that x is even does not imply that all natural numbers are even. Hence, this implication is not valid. So we cannot apply the deduction rule, a deduction rule of the form that we had for propositional logic, without any qualification or conditions. So in order to state an appropriate qualification for our deduction rule, we have to define a notion of dependence of one formula on another within a deduction. So we'll assume we've got a given deduction, a given proof. proof, of course, is really just a sequence of formulas. Say B1, B2, and so on up to Bn of a formula B from, say, a set of assumptions U union a singleton containing only the formula A. We'll say that one of these formulas, Bi, depends on A if either, this is a recursive definition, so the simple case is where Bi is A itself, or 2, Bi is inferred via either of our inference rules, so MP or gen, from earlier formulas in the sequence. So in other words, Bi isn't an axiom, or it isn't, and it isn't an assumption. It is inferred from earlier steps in the proof. And at least one of those formulas from which it is inferred itself depends on A. So intuitively, Bi depends on A if A was used as an assumption in proving Bi. Just as using the inference rule gen here, we can prove for all xa from A. Okay? But then in our proof, for all xa depends on A. If we simply invoke A as an assumption and then apply generalization, then this formula for all xa depends on A in our proof. And we have to rule out that kind of situation. So with this definition of dependence of a formula in a proof on A, we can state a valid version of the deduction rule. So before, our deduction rule assumed that we could deduce B from our set of assumptions. Namely, the union of the set U with the singleton containing only the formula A. But in this case, we have to assume something about the places in this deduction, the steps in this deduction where we have applied the gen inference rule. We have to assume that no application of gen to a formula within our deduction that depends on A has as its quantified variable because when we apply gen, what we're doing is adding a universal quantifier for some variable x. So that variable x, say, must not occur free in A. then we get the usual conclusion of the deduction rule, namely that we can discharge the assumption A and conclude that we can deduce from the set of assumptions U the implication A implies B. And like the earlier deduction rule that we had for propositional logic, this can be proved by induction on the length of the deduction of B. I'm going to leave that as an exercise. So I'll let you generalize the deduction rule to the first order logic case, making use of this notion of dependence of a formula on A within the given deduction of B. Now, that statement of the deduction rule may seem a bit complicated. You'll need to go over it a few times probably to make sure that you have it straight in your head. Fortunately, we can often use simpler versions. So we have two corollaries. First corollary reads like this. Suppose there is no application of gen anywhere in the deduction of B that has as its quantified variable a variable that occurs free in A. Then the condition in our deduction rule is satisfied automatically. We don't have to worry about that notion of dependence. So suppose that there is a deduction of B from our assumptions U union the singleton A, in which no application of gen has as its quantified variable the quantifier, the variable rather that appears in the universal quantifier that you're adding, a variable that occurs free in A. Then we can, in fact, discharge our assumption A and conclude that we can prove from the assumptions in U that A implies B. We can deduce A implies B from those assumptions in U. So in fact, if in fact we never apply gen in such a way that the quantified variable x, in for all x A, is a variable x that occurs free in A, then we can go ahead and assume the usual conclusion of the deduction rule. And the other corollary has to do with the fact with the case where there are no free variables in A. So the second corollary is if A is a closed formula, and there is a deduction of B from the assumptions in U union the singleton A, then we can go ahead and discharge the assumption A and conclude that we can deduce from U A implies B. So that's our modified deduction rule, together with two simpler versions in the form of these first two corollaries. Let's just go over that once more. So we have this notion of dependence of a formula bi that appears in a deduction of b on a. Essentially, bi depends on a if a was used in deducing bi. In that case, our deduction rule reads as follows. If we have a deduction of b from the usual assumptions, the union of u with a singleton containing only a, then as long as there is no application of gen in that deduction to a formula that depends on a, where in that application of gen the quantified variable is a variable that occurs free in a. As long as that is the case, then we can go ahead and discharge the assumption a and conclude that we can deduce a implies b from u. But that's only the case if in our deduction of b from these assumptions there is no application of gen to a formula that depends on a, where the quantified variable in the application of gen, the one that is written as x in our statement of gen, where that quantified variable occurs free in a. As long as there is no such application of gen, then we can go ahead and we have the usual conclusion of the deduction rule. And more simply, that means that if nowhere in our deduction of b from the usual assumptions there is an application of gen that has as its quantified variable a variable that occurs free in a, then we don't have to bother applying the notion of dependence. The condition in the deduction rule is automatically satisfied, and we can discharge the assumption a and conclude that we can deduce this implication from u. And the second case is very simple, where there are no free variables in a. A is a closed formula, in which case we have exactly the sort of deduction rule that we had in the propositional case. If we can deduce b from these assumptions, then we can discharge the assumption a and conclude that we can deduce a implies b from the set u. So that's probably one of the biggest changes in going from propositional logic to first order logic. Pretty much everything else that we did in the deductive system for propositional logic carries over to the first order case. We just have to be careful about the deduction rule where applications of the generalization inference rule are involved. Now in the notes there's a section 9.1, first order logic with functions, meaning with function symbols. I think for the sake of time we will skip this. Following that, there is a section giving some theorems of the deduction rule, of the Hilbert system. It is actually numbered 8.4 because that's its numbering in the textbook. Proofs of theorems in H. I think it would be tedious for me to go through all of these in a lecture, so I suggest you read this section yourself. It's simply a series of theorems in the Hilbert system and their proofs, which are generally pretty short. So I don't think there's much point in my going through those in lectures. And with that, in fact, we pretty well conclude the main substance of the course. That is, we've concluded all the material that you're going to be responsible for in any deliverables. There are still some important things to say, and I will say those in subsequent lectures, but those are not really things that I can examine you on, perhaps especially in the present circumstances. So let's just say that the material you're going to be examined on ends at this point. In the next couple of lectures I will talk about strong soundness and strong completeness. The proof of strong completeness is more complicated, obviously, in the first order logic case, but the main ideas are the same as those in the propositional logic case. That's why we went over the proof of strong completeness in some detail in the case of propositional logic. We'll cover it in a more high-level way for first order logic. After that, there's another topic that I'd like to discuss that sort of goes back to the topic of undecidability, with which we began our discussion of first order logic, and that is known as Hilbert's first incompleteness theorem. Again, that relates to the issue of decidability. So I'll talk about that in another lecture, but you won't be responsible for that in assignments, quizzes, or the final assessment. So I'll see you in the next video, which will talk about strong soundness and strong completeness.